Hi ladies and gentlemen, this is Mr. Green, and once again I am doing some star testing this week. I know, it's one of those things where I can't get out of it, so I've got to be there. So, I'm not going to be able to be in Class Connect, but I do want to make certain that I give you this video to go over some of the things that you're looking at. What are we looking at? We are looking at some very strange things right at the moment. Okay? We're looking at a type of geometry that is not Euclidean geometry. It's called non-Euclidean geometry. Non-Euclidean. It's types of geometry that don't deal with flat surfaces. Okay, everything we've done so far in geometry has been Euclidean geometry. We've always dealt with a plane or a line or a point or something like that. Well, when you get away from dealing with those Euclidean concepts, you get some really strange geometry that you start looking at. And you need to understand how this non-Euclidean geometry fits into the world. That's why we're covering this stuff right at the moment, okay? So what do we start with? We start with this thing called the golden ratio. The golden ratio is something that we find in nature all over the place. So if you're in biology, you probably saw the golden ratio and didn't know about it, okay? It's this ratio right here. It says A plus B, the quantity of those two things, divided by B is equal to B over A. And what you see is, if you remember in the lessons, they showed you a nautilus. And that was that spiral that goes around like this. Well, if you look at it, the squares and things, they grow in this type of a ratio. Okay? Well, what do we do? How do we solve problems like this? Oh, got a cough. Hang on a second. Okay, sorry. How do we solve problems like this? Well, you're given two sides on a rectangle and asked to find this side up here if this one is in a golden ratio, if it's in a golden rectangle. Well, what you do is you stick the 9 in. It's the smaller number. It goes in for the A. Okay, the B we don't have, that's X. It goes out here for the other one, and then you just do a little bit of cross multiplying, or means and extremes, however you want to look at that. You get X squared, because these two multiply together, X squared, and then 9 times 9 is 81, and 9 times X is 9X. Well, I subtracted those from these two from this side, and got X squared is equal to 9X minus 81. I can't really factor it, so I'm going to have to use the quadratic formula. Negative of negative 9. Why did I do that? Well, that's B. B was a negative 9, so I had to use the negative of negative 9. Plus or minus the square root of negative 9 squared, B squared, minus 4 times A times C. All divided by 2. Well, that's 9 plus, and when you work out this stuff right here, you're going to get something like 20.12. So 9 plus 20 is 29 divided by 2. It turns out to be about 14.56. So I would say that this side over here, if this were a golden rectangle, would be 14.56. Now you know what? Going through all of this, difficult. I understand. It's not an easy thing to do. I use this, 8 over 5. 8 over 5 is that golden ratio, and it's simplified for you. I mean, the value is like 1.6, and it's a never-ending decimal, and it's really difficult. And the only way to really do it is with this quadratic formula. But if you use 8 over 5, it comes out to be about the same. 8 over 5. 8's the big side, 5's the small side. Big side, small side. X over 9. 8 over 5 is equal to x over 9. Well, means and extremes. 72, 5x divided by 5, 72 divided by 5 is 14.4. Look how close I got just by using that ratio. Easy way to estimate what the value is. And if I'm told it's in a golden ratio or golden rectangle, either one of those two things, it's real simple to just use this 8 over 5 and get you a number that you can work with. Okay? So the next topic in non-Euclidean geometry is taxicab math. Taxicab math? What the heck are we talking about, Mr. Green? Well, early on in the whole geometry course, we taught you how to find the distance. And once you found the distance, you knew the distance formula. It was that square root of x minus x x2, x1 minus x2 squared, plus y2 minus y1 squared, and you take the square root of that whole thing, and it's a little bit of a difficult process to go through. What we discovered was that taxicabs can't go in a straight line between two things. This is as the crow flies. So if I were trying to find the distance from A to C, from here to there, I could go straight across there. But, the whole point is, if you're in a taxicab, at least in this century, you're in a taxicab, you can't go through the blocks like that. You got to go around them. You got to go around the buildings. So you got to go up and then over and then up and then up and then over and then up and then over and up and up and up and over and over and up and over and then up, and you get to your location, right? And the way you do taxicab math is it has to stay on the lines. And then you can just count the number of lines that are there. Well, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10, 11, 12, 13, 14, 15. The distance between those is 15. That's the way taxicabs compute their costs, because they do it based upon the number of blocks that you go or the number of quarter miles you go or something like that. They have a rate per quarter mile that they charge you. This is what you need to know how it's done if you're ever in a taxi and you want to figure out how far they're going or how much you're going to get charged. Is how you stay on those streets and still get to where your location is going to be. Okay? Well, they do something slightly different with that as well, because if we can do distance, we can do a circle. Remember, a circle is located at a spot. So if I start right here and I wanted to find all the points that were equal distance from point D, that's a circle, right? That would have a radius of 3. That means they're all going to be 3 units away. So I could go 1, 2, 3. Well, there's a point right there that's 3 units away. And if I go here, 1, 2, 3, there's a point there that's 3 units away. And 1, 2, 3, there's a point there that's 3 units away. And 1, 2, 3, just off the screen there. There's one that's 3 units away. Doesn't look much like a circle, does it? But you know what? 1, 2, 3, 1, 2, 3. Look at this. Isn't this a strange looking little combination of points? All those green points are a circle. Well, it doesn't look like a circle on the screen. It looks almost like a rectangle. Yeah, it does almost look like a rectangle, but remember, they're individual points. They're not connected to each other, okay, like you do see in a normal circle. But these are all the points that are equal distance from point D. As a matter of fact, they're all 3 units away from point D there. And that would be the circle that you would get around point D that's 3 units. That's the exact definition of a circle, equal distance from a point. And that's what we did. We found the equal distance points in taxicab math. See how it looks a little different? It's different because it's non-Euclidean mathematics, okay? And this is what a lot of times taxicabs use this type of stuff. They locate themselves right here and they say, okay, I can take you, I know what the set amount is going to be to here, so that's the same going to be there or whatever. I mean, they can give you the cost of moving from one location to another, and it's just a set rate. Okay? It's brought up because it is something that is different. It is non-Euclidean type mathematics, and that's why we're bringing it up and talking about it. Okay? The next topic we're going to look at there are called paths and circuits, and they talk about a Hamiltonian path and a Euler path and circuits and things like that. The difference is that paths just go and hit all the points, and circuits will hit all the points and yet wind up at the same spot in which they started from. So let's just look at a couple of these. If we were going to look at this first one here, A, it starts at A and it goes to B. So it goes up here to B. And then it goes to C. And then it goes to D. And then it goes to F. And then it goes to A. Did that hit every one of the routes? All the lines? No. Did it hit all the points? No, it didn't hit all the points. It left E out of it, didn't it? So I don't think that we would call that a good path because it didn't hit all the points that we wanted to hit, but it did go around the circle a little bit there. Let's try a different one here. Let's see here. The one that I think is correct is going to be this one here, C, because I can see the letter E in that one. Let's try that one, okay? So it starts at F and it goes to D, and then it goes to C, D to C, and then it goes to E. I think you got E in there this time, right? And then it goes to A, and then it goes to F. Did we hit all the points on that one? No. Still left B off of this one, didn't we? Jeez. Okay, well, let's try another one here. Let's try D down here. It starts at D and it goes to A. D to A, that's good. To B. Well, now we got B in this one. To C. Okay, this is looking good. To E. Yes. And then it goes to A. And then it goes to F. Hey, we hit all the points. Okay? We hit all the points in this one. So it is going to be a good path. Okay? Now, if it starts and ends at the same location, then it's a circuit. Now, they're going to tell you in the lessons how you can use and find the degree of each one of the points. And then there's a mathematical formula you can use to determine if it is going to be a circuit or not. Because if it has a certain number degree at each one of the points, then you will be able to say that it is a circuit or a path. And that's what you have to be able to look at sometimes. Okay? Let's look at this next problem here, though. The reason that these have come up has been UPS, Federal Express, US Mail, the ice cream man. They all want to do certain things. They want to start at a certain spot at their warehouse, travel the shortest distance possible, and wind up at the same spot again. Okay? So, like if this was a mail carrier, parks his truck right here. He wants to walk the shortest distance he can and hit every one of the streets and all of the points. Okay? So if he goes like this, down to here, and over to here, and down like this, and over and up, see how I'm hitting all the points? So let's see here. What was his distance that he actually traveled there? Well, he went 4, 8, 12, 16, 20, 24, 28, 32, 36, 40, 44, 48. He went 48 units, whatever this is here. That's the way you'd get this. Now, what would be a non-shortest distance? Anytime I had to go over the same thing twice, like if I started at A there and I went down to here, went around that box, and then I have to go over A to B again, obviously I'm not getting the shortest distance, am I? Okay, so I've shown you one possible way and one failing way to get there. Okay, you have to be able to come up with these things to make them work. This type of mathematics that we're looking at right here, these circuits and paths, are used by all of the transportation companies, all the bus routes, all the train routes, all things like that. It's used by all of the carrier companies like airplanes and airports and uh, Federal Expresses and UPSs and mail carriers and everyone like that to try to plan out routes to get people where they need to go, to get them to go around the routes and yet still cover everything that needs to be done. There's a whole field of mathematics that deals with this, okay? Just wanted to make certain you're aware of it. Another field of geometry is called topology. Topology is where we are looking at things that are similar in shape because they're the same object, just twisted or turned or rotated or manipulated in some way. If you look at this object 0 right here, okay, it gets manipulated a little bit, okay? If I were to make it into circles at the top here, it would look like figure 1. If in the process of getting there, it might look like figure 4 because I'd have these rounded ends and square sides on it still. Okay? If I brought this and folded it around on the outside of this one here, it might look like figure 2. Never will it look like figure 3. I want you to notice, how many vertexes do I have? Well, 1, 2, 3, 4, 5. You don't see vertexes in circles, but it's still an odd number of vertexes, right? In this one, I've got 6 vertexes, but if one of them were the same as that corner up there, I'd have 5. Okay? And on this one, I've got 4, and on this one, I've got that 1, 2, 3. I got 5 on this one too. Vertexes might help you locate them and see what's going on there. There are many different ways to look at topology. Topology is simply the twisting and the turning of the objects, okay? And if they are equivalent topologically, golly, there's a word for you. If if items are equivalent topologically, then you can get certain information about the object based upon that topology. One of the things that you get in this particular section is this one here about the Jordan curves. Okay, Jordan curves are when you try to stay inside of a maze or outside of a maze to try to get to a certain point. Well, you also have these situations where the gas lines and the electric companies and the sewer companies and everyone else wants to get their service into a house. And how do we get all these into a house without crossing over each other? And that's one of the big things that comes up, okay? If I connected the gas strictly here to 2, like that, house 2 to that gas line, can I go from the electricity to house 2? Is there any way to get there? Well, electricity is already there. Can I get from the water? Yeah, let's see here. Oh, I'm sorry. Can I get my electricity to house 1 is what I'm asking. Because see, if I try to go through the inside in here, I'd have to cross over the gas line. I don't really want to do that. Well, yeah, what if I did this? I get electricity over here to the house 1 like that. How do I get water to house 3 then? I can't go over the electric line. I can't go over, these other lines inside here. You cross over the gas line. Well, that's where you got to go all the way around the outside, right? That sure seems like well, going around the outside's not going to get me there, is it? How can I get there? Water to house 3. This is a very complex type of problem. These type of curves like this, it's called a Jordan curve, okay? You've got to be very, very careful with it, which ones you put in place first, which ones you put in place second, and so forth, okay? One thing you might do is, yes, I might connect house 1 to the electricity this way, okay? And I might connect water this way, okay? And then take the gas line and go a different route for the gas line, see if we couldn't get to house 1, house 2 that way. Well, this way I'd still be crossing lines, wouldn't I? Let's try a different route. What if I did the water this way? I do from house 1, I got to get to the electricity. Well, I'm going to go around the outside to get to the electricity to house 1. And pin like this. Okay? And to get to gas, I'm going to, I'm still stuck, aren't I? Is there any way of getting there? I want you to work on this for a little bit, guys. Think about it. Is there any way with the lines that are there, without crossing things, because we can't really cross other lines, come up with a way of connecting these? Think about it for a while. There are ways of doing those type of things. That's the whole thing with topology and the Jordan curves. Now, one of the fun ones that you get involved with is the spherical geometry. This is the geometry of the Earth, okay? Now, you thought we were dealing with the geometry of the Earth, we were dealing with the Euclidean geometry. Well, on a small scale, it is because the Earth looks flat in a small scale. And the Euclidean geometry, all the geometry we did, works for a very, very flat surface or a reasonably flat surface. But when you start talking about geometry of the actual Earth itself, a couple things come into play. First of all, there's a great circle. There's one circle that goes all the way around the Earth. Right now, if you think about the Earth equator goes around the circle, around the Earth. That is the biggest circle that can go around the Earth, that sphere. I know the Earth's not necessarily a sphere, it's kind of oblong in shape, but we're going to assume that it's a spherical shape, okay? That great circle, that one right at the middle of the sphere is called a great circle. All the rest of these are just, they're just circles that go around the Earth. There are no straight lines any longer, right? So can I have parallel lines? Well, you know what? What if I had parallel to look at the longitude lines on the Earth? Longitude lines are considered to be parallel, but you know what? They intersect at two different locations, one at the North Pole and one at the South Pole. So longitude lines on the Earth aren't really parallel, are they? They're really intersecting lines. But if you look at them in a short space, in a limited size, we consider them to be almost parallel to each other. Another thing that you wind up in spherical geometry is, remember how triangles added up to 180 degrees? And they no longer add up to 180 degrees any longer. Okay? We could have a triangle on the Earth, on the surface of the Earth, that has up to three angles that are almost 180 degrees. And that's really weird. But you know what? That's one of the things that you wind up with when you wind up with curves that are now considered to be straight lines. And that's what you need to look at that when you're looking at the spherical geometry. Make certain you're understanding all the aspects of that one, okay? Now, there is a couple of terms in that one that are kind of important. One of the ones you're going to wind up with is, what's the shortest distance from New York City to Hong Kong? Well, the shortest distance is going to be that circle that goes around like that, right? That's called a geodesy. That's what they call it because it goes around the Earth. It's geodesic. It goes around the Earth, okay? So the shortest distance would be called a geodesy, and that's a term you need to make certain you get hold of. Okay? And lastly, the final topic I want to talk about here is the fun one. It's called fractals. Fractals is a form of mathematics that they've started in recent years because they've noticed that the Earth and in nature, we can wind up with these types of things called fractals that actually do a better job of drawing and viewing things that are naturally occurring than what we can do with uh, other other techniques. It gets more accurate and it looks a little bit better than what we could come up with in other ways. Let me give you an example. Uh, one thing that they have done is, if they look at the MAP making process, it is much easier for them to use fractals to draw the edge of a surface, like the shore of a lake, than it is to try to draw it out any other way. Okay? It becomes a little bit more accurate that way. So let me just show you what's going on. If I have a rule that says I'm going to cover the center of a square with a spot. So I've got this square here in step 0, and I cover the center with a spot. And then I go down and I look, well, where is another square that I could cover? And I look at this littler square here, and I cover the center of that square with a spot. Well, if I wanted to take it to the next level, I'd be covering each one of these squares here with a spot. And that would be step 3. You see what I'm doing? There are several different fractals that are talked about in the lessons. A couple of them are kind of cute. Okay? You might experiment with them, see if you can't have some fun drawing some fractals, seeing how they work. Okay? What it amounts to is just uh, series, sequences, things like that. That's where this whole concept of fractal mathematics came from, was out of the series and sequences and things that were in mathematics that we have studied in other grades, but we're not studying in geometry. Okay? Do you see how I'm getting that here? I think you'll be able to see fractals once you get into it. Now, this has been the Class Connect for Geometry. My secret word for today is dolphin. If you are watching this, make certain you send me that secret word in a K-mail so that you get credit for having watched this. What we're doing is we're looking at non-Euclidean geometries. Okay? Why? Because Euclidean geometry is good in a world that we live in on a small scale. But when you start looking at bigger scale, Euclidean geometry starts giving you all sorts of problems. And so we had to go to other types of geometry, like spherical geometry. And in a real world, Euclidean geometry gives you the distance between 2 points. And we had to do things like taxicab geometry. Okay? So hopefully that gives you a good idea of what we're talking about and the geometric concepts uh, of the real world. Okay? I look forward to seeing you. We do have finals coming up soon, so watch for my review sessions that I'll be having. I should see them in the announcements here in the next day or two. I will talk to you later.